Episode, we are going to look at energy balance. Now is the time to dive deep into thermodynamics. Do you remember the first law of thermodynamics, which states that energy can neither be created nor what? Destroyed. Meaning within a system, the amount of energy or the energy content within a system can neither be created nor what? Destroyed, but can change form from one form to what? The other. Today's episode and the analysis is going to be different. Pay attention. So, a major consequence of the first law is the existence and the definition of the property total energy. The conservation of energy principle can be expressed as now. We want to restate the conservation of energy principle. The net change, that's the increase or the decrease in the total energy of the system during a process. So the total change in the energy of a system during a process, if this system is undergoing any process, then the total change here is equal to the difference. Pay attention. The difference between the total energy entering and the total energy leaving the system during that process. So what we are trying to say is that the change in energy here is equal to, if this system is undergoing a process, then the change in energy is equal to the difference between the energy, this is energy leaving, and this is energy entering. So if you find the change in the total energy within the system is equal to the difference between the entering and the leaving. And I think this is true. Are we good? So if we want to know the total energy within a system, then we strike the difference between the energy entering the system and the energy leaving the system. Are we good? All right, so let's look at the equation. Therefore, total energy entering the system minus total energy leaving the system is equal to the change in the total energy of the system. Are we good? So we assume that always energy entering the system is greater than energy leaving the system. Because, for example, if this system is undergoing a process and it is doing some work, if the amount of energy coming out is greater than the one entering, with time, this system will collapse. Are we good? So we assume, and it is good for us to get energy entering the system greater than energy what? Leaving the system. And this is the first equation we are establishing, that anytime energy inside our system minus the energy outside our system should be equal to the change in what? The total energy of the system. So let's assume the energy entering is what? 50 kilojoule, and the energy leaving is what? 25 kilojoule. Are we good? Then our change in what? Energy within the system per time will be energy entering, which is what? 50 kg minus, this is just giving you understanding of the equation, kg. And our change in energy for the system, if we are running it per hour per second, will be 25 kg. Are we good? So this is the change in energy. Yes, to know the amount of energy staying in the system, you have to get the amount entering. Remember, energy can what? Enter into what? A closed system in the form of what? Heat and what? Work. But if it is an open system, then mass can also what? Enter. So these three are the forms through which energy can what? Enter and leave our system. But the first two, heat and work, is for closed system. Open system has mass what? Added. So generally, this is our first equation we are establishing, that change in energy of any system, closed or open, is equal to the energy in minus the energy out. And it is going to help us in our analysis. Change of a system. So let's continue with the analysis. So we know that energy change is equal to energy at final state minus energy at what? Initial state. So if it is undergoing a cycle to, then our change in what? Energy will be what? The change in energy will be the final energy minus what? Energy what? Initial. We also assume that the final energy is greater than what? The initial energy. And look at this. If it is a cycle, then the change in energy will be what? 0, because the final will be equal to what? The initial. Are we paying attention? So change in energy of any system is given us. So first equation, we got change in energy of a system is equal to energy what? In minus energy out. That's one way. What if we have final and initial what? Energies? Then it will be energy final minus energy initial, which is E2 minus E1. Are we good? All right. We also have this equation. We know that the total energy within a system is a summation of what? The internal energy, the kinetic energy, and the potential what? Energy. We've already established this equation as our equation 3. So let's further break down this equation. Note that energy can be transferred into the form of what? Heat, work, and mass. Mass is now added because now we are considering both closed and what? Open system. Bear in mind, if the system is what? Opened, then energy can now go in or out of the system, heat, work, and in the form of what? Mass. But if it is closed, we only consider heat and work because mass is not coming out from what? Closed system. Are we good? So now we want to combine all the systems, both closed and what's open. So we are considering the 3. And that the net transfer of a quantity is equal to the difference between the amount transferred in and out. So now let's consider these 3 things that can come in and out of a system. Meaning if this system is undergoing what? A process, then the change in energy of this system will be as a result of this 3. Are we good? The change in energy, because the things that can cross the boundary, remember we are considering it to be both closed and what? Open, the general one. Meaning the 3 things that can cross the boundary to cause a change in the energy are these 3 things: heat, work, and mass. So as this equation is what? Saying we can find the change in these 3 things to also get the change in what? Energy. Is it making sense? Yes. Therefore, our change in our energy within a system is equal to the change in the heat, K is representing the heat, plus the change in the work done, plus the change in mass. If these 3 things are those possible ways of what? Causing energy loss or energy gain within a system, then anytime we want to know the change of energy within the system, we are going to consider these 3 major what? Forms. Are we good? So if I want to know change in what? The energy, the same as energy in minus what? Energy out. Established. What about change in heat? It is heat in minus heat what? Out. Always we consider the in to be greater than what? The out. So, but it can change. Heat in minus heat out plus work. Change in work will be work in minus what? Work out. And what about mass? Energy of mass in, energy of mass what? Out. Are we good? And they are all equating to what? The change in what? The system, which is energy in minus what? Energy out. So this will be energy in minus what? Energy out. So when you are given a question or a problem, you have to first get in mind these equations. That is going to what? Help you. So heat will be what? Heat in minus heat out. What about work? Will be work in minus what? Work out. What about energy mass? Energy of mass in minus energy of mass what? Out. So this is the another established long equation in what? Thermodynamics that we are going to use mostly, because when you consider any system, these three things are influencing the change in what? Energy. And it is good we have this equation what? Written. So we have this equation and the other forms of what? Equation in mind. But please bear this in mind the most. Change in the heat, change in the work, and change in what? The mass. What if there is a rate form? Another equation is what we call the what? The rate form. Are we good? Where we have the rate, change in energy with respect to time. We talk about rate. If it is respect to time, then change in energy, which is the E on the T, will be the same as in minus what? Energy out. And we already know energy in minus energy out can be also this one. Are we good? So we can bring all this here to get, but remember you use the rate form when your parameters are given in what? Kilowatts. And this mostly in what? Kilojoule. Are we good? Very simple. Let's move to the next page and make all the deduction over there. So the necessary deduction. So throughout this chapter, how many equations are we having? So first, we know that energy within a system is the summation of the internal energy plus the kinetic energy plus the potential what? Energy. Are we good? We also know that our second equation is change in energy is equal to what? Energy in minus what? Energy out. Are we good? And energy in and energy out are in the form of work. They're in the form of work, heat, and the form of what? Mass. So energy in minus energy out of a system is the same as change in the work done plus change in the heat and the change in what? Mass. So I can further reduce this to energy in, energy out equal to, let me start with the heat, Q in, Q out plus work in and work out. So what about energy of mass in minus energy of mass what? Out. Are we good? And our fourth equation, if it is in the rate form, if we are considering the rate form, we will solve example, you see. Then our change in energy, which is the same as this, the E, the T, will be equal to what? Energy in minus what? Energy out. Remember, it's a rate form. Energy out. Are we good? Okay, so very simple. And a situation where the system is stationary and kinetic energy, so fifth equation, this we got it this way: E is equal to U plus kinetic energy half mv squared plus potential energy mg, where z is what? The height. So for stationary systems, we know that v is 0 and what? Z is what? 0, the height. So this can be reduced to E is equal to our internal energy half, or this will be 0, so it will be gone to 0 to approach 0. This will also go to 0. So our E now is also equal to change in what? Internal energy. But where I want you to pay attention to is the fourth equation and the third equation. They are those we are going to use most in our energy analysis. Understand this, and thermodynamics, you are true. Are we good with the equation? The next episode, we are going to solve 4 examples under this chapter. We are doing the video in 2 forms, so check out for them. First set of the problems will be 4 questions, and the second set will be 4 questions. Thank you for watching.